Good afternoon. Welcome to our session on atmospheric and subsurface radionuclide background and dispersion. My name is Jolanta Kuśmierczyk-Michulec, and together with Man Sung Kim, we will co-chair this session. So it's our great pleasure to co-chair this session. We will have 5 presenters. So this is our oral part and poster presentation. The lighting session is on Thursday, and posters are on Friday. So with this, I would like to welcome our first presenter, who is Pierre Adler. So the floor is yours.
And for the traffic control, we'll try to give you a warning at 10-minute mark.
Where is the little bar? Okay, thank you. So, hello everybody. So, can I see my talk? Yes. So, the purpose of this work was to study several additional tracers in addition to the traditional xenon, such as water, radon, and CO2, and to possibly observe emissions of these additional tracers at the test site, and also to combine these observations with the observation of radio xenon at the monitoring site. So the configuration is the following. This is the test site underground, so you see the ground surface. Below, you see the cavity, the chimney, and the magma created by the explosion. And these are simplified in this model. We could do everything, but here it's simplified as a medium of high permeability and high porosity. We have an embedding porous medium with a much lower permeability, a much lower porosity, and a fraction network, which is partially or totally created by the test with 200 or 400 fractures of large fractures of a radius of about 20 meters. At the top, at the ground surface, we include fluctuating atmospheric pressure with an amplitude of about 1,000 pascals and a period of about 1 week. So, yes, the modelization, it is based more or less on the paper which is cited here. So the porous medium, we use Darcy equations, 3-dimensional for the flow, energy, and tracer. For the fractures, we use 2-dimensional equations on the Darcy scale as well, for flow, energy, and tracer. Plus, we have to take into account the exchanges between the fractures and the surrounding porous medium. Numerical, we mesh the fractures by triangles. We mesh the porous medium by tetrahedra. We discretize the equations by finite volume technique, and we solve the equations by conjugate gradient techniques. Everything is parallelized by OpenMP. Results, we are going to show 2 kinds of results. One at the test site for an hypothetical explosion of 150 kilotons buried at about 550 meters. And at the monitoring site, which is supposed to be 1,000 kilometers away from the test site, it includes a delay, a travel time of 1 day, and a dilution factor, eta, which is close to 10 to the power minus 17. So the outputs, we are going to look first at the outputs at the nuclear test site. So for water, we take the initial mass of water, which is contained in a cavity, which is described here. And we have a fractured porous medium with about 200 fractures, a porosity of 5%. And we study systematically for three initial pressures in the given conditions of 50, 100, and 200 bars. So the mass flow rate at the ground surface, of course, is given here as a function of time. The total mass transferred to the atmosphere is given on the second graph, again as a function of time, but you may be more interested in what happens at the beginning. So in the first 12 hours, you have this total mass, which is transferred now, and this has to be compared with, say, as an order of magnitude in a column of about 1,000 meters high above the test site, which is 200 by 200 meters. You have about 600 tons of water. So is that detectable by satellite imaging? This is a question. Next, we made systematic studies of the influence of the petrophysical properties, but I don't want to detail them here. Just two sentences. When the porosity decreases, the initial mass flow rate increases. When the number of fractures increases, the initial mass flow rate increases. So these are some of the results. I just want to say a few words about the comparison with an homogeneous medium. So we can replace the fractured porous medium by an homogeneous porous medium with equivalent permeability, and we keep the same porosity. If we do that, we obtain these results here for the mass flow rate and the total mass transfer. And what you notice is that here you have a delay of about 1 day, a little bit more than 1 day, which is the delay to fill in the porosity by the compressed gas. If I compare the two models, the full one and the homogeneous one, on one hand, they are quite different. On the other hand, you see that the orders of magnitude are conserved, so it's not so bad. Now CO2, we assume that CO2 is contained in a 10-meter thick soil layer at the top of the medium without any fractures. So some properties of this layer are given here: high permeability, high porosity, and so on. Mass flow rate, a typical mass flow rate is used, and there is no source term in these preliminary calculations. So what we have here, the total mass transferred, what you see below, you see the atmospheric pressure fluctuations, not to scale, of course, just to show you how it goes, and you see that these fluctuations are seen actually on the total mass transferred. You have some undulation on that. Now, additional CO2, which is transferred to the atmosphere. What is important is the difference of what is due to what is done by the test and what is usually transferred to the atmosphere. So we subtract one to the other one and get this result. So this is the additional mass. And this has to be compared with the mass transfer to the atmosphere, for instance. During 12 hours, you see it's about 150 kilograms. So again, this kind of quantity of about 2 tons in 2 days, is that detectable? That's another question. So I want to I want to show you that the flux of CO2 at the surface is not uniform because the fractures stop 10 meters below the surface, but you can see still the influence of these fractures on the outputs, though it's smoothed out by the soil layer. So now we are going to see two examples of outputs at the nuclear site and at the monitoring site. The first one is radon, but I go very quickly with this. So at the test site, you have a contribution of a radon originated in the porous medium, the thin line. The medium line is the radon originated in the cavity, and the thick line is the sum. And then at the, at the monitoring site, with 6 hours sampling, you get something like that. And when you look at the ordinate and see 10 minus 8, then you see that it's totally hopeless to measure that. Note that it's not 50 becquerels per second, but 50 becquerels per cubic meter. Now let us go to xenon. So we assume that in the cavity, 1 mole is produced, and that there is a dilution coefficient, as I said, about 10 minus 17. So here is the activity at the nuclear test site. So you see on the top scale, 1 minute, 1 hour, 1 day, 1 week. And at the monitoring site with 6 hour sampling, the activity concentration, which is given as a function of time again. And the green curve, green line that you see is the detection limit, which means that it should be detectable. So we have concluding remarks very quickly. Radon cannot be detected at the monitoring site. Water and CO2 could possibly be detected depending on sensitivity of satellite imaging. And then finally, xenon should be easily detected 1 kilometer away if the atmospheric conditions are favorable, of course. And with this, I want to finish my talk and thank you for your attention. Thank you.
Thank you very much. Now it's time for questions, so please take the floor.
Given no question, let me ask one question.
Yes, please.
So, speaker, you compared equilibrium model and then discrete fraction model to predict or to estimate the release from underground system, but both are modeling-based simulation, right?
Yes.
And fraction modeling using Darcy approach is potentially of a concern because sometimes, depending on how fracture is formulated, discrete fracture modeling without actually using Darcy is necessary. So if your fracture system, I mean, if the site-specific nature of the fracture requires sort of discrete fracture modeling, how the result could be different? Any thoughts on that?
You mean between the fraction model and the homogeneous
the fraction
model?
model you have used is still based on Darcy approach.
Yes.
And that may not be applicable if you have a very different type of discrete fractures. So if that is the kind of site-specific situation, how would you see the difference from that?
Between two different fraction networks. Huh?
Yeah, very sparsely located fracture, if you have such thing.
We have made a study. I made an allusion to it. We have made a study also with when the number of fractures is doubled. And so of course, there is some difference in the results. But the system is such that once you have to generate the fraction network or to measure them and to put them on the computer, and then everything is automatic. You can discretize the equation, discretize the medium, discretize the equation, solve the equations in a totally automatic way, if it is the.
So you think still the result,
yes,
regardless of maybe fracture types or situation, the ballpark, the magnitude of the result would still be captured by the current modeling?
I guess so, yes, within the.
So the conclusion you made still should be valid regardless of the site-specific situation?
I guess so, yes. Yeah.
Thank you. Yes.
Please take a microphone.
Thank you. If we focus on Xenon, how much of Xenon will released compared with the amount of generated? What's the percentage?
With the amount of gallery,
The generated by the nuclear explosion. What's the
can you get the,
percentage?
can you get that?
I think he was showing 10 to the minus 17 or something. So very, very small fraction is released.
I know.
Yeah.
I want to know the number. What's the percentage of released by the underground nuclear explosion? Then do you simulate in the simulation? Do you get a number? The percentage.
Percentage.
Yes. Yes, compared with all the amounts.
Well, this is calculated in, I will give you the results of that if you want, because I have what is initially inside the cavity, and then I know what goes out
Yeah.
of the medium. And I have also, of course, somewhere to make some check what is inside the medium.
Yes.
So at the beginning, you have a little percentage tracer which will go out. And it's mostly conductive in most cases, for instance for xenon, because xenon is contained in the cavity, so the flow will carry out, the flow of gas will carry out xenon. But this is not true, for instance, for CO2, because the situation is very different. It's in a third layer of the organic space. And now it's very different. And for Raven, it's another story, because part of it is in the cavity, and part of it is in the core. So it's a mixed space.
Thank you.
Thank you. Thank you very much.
So we have maybe time for one more
One more
short
question?
short question.
Thank you for your presentation. Have you given any thought on how to distinguish the CO2 and water signatures from an underground nuclear explosion from some other large-scale underground explosions?
No, this is beyond this is beyond my skills, you know. I am of a fluid mechanics background, and I don't know how to do such things.
Okay, thank you. In the interest of time, we'll move on to the next presentation. So next speaker comes from Pacific Northwest National Laboratory, Mr. Johnathan Slack, spending 6 years as a physicist in doing modeling of radionuclide release from molten salt reactors. His title is Potential Impact of Molten Salt Reactors on Radionuclide Stations of the International Monitoring System. Mr. Slack.
Thank you. So, good afternoon. I'm here to talk about the potential impact of molten salt reactors on the radionuclide stations of the International Monitoring System. So, by way of an overview of this work, molten salt reactors are a type of Generation 4 nuclear reactor that have been experiencing a bit of a renaissance. They differ from traditional reactors in that traditional reactors have solid fuel pellets arranged in columns in your fuel rods. Molten salt reactors have molten salt into which you directly inject your fuel. This provides an opportunity in a molten salt reactor to refuel or reprocess or clean up the fuel salt while you're still operating, while you're still producing power. We focused on simulations for 4 broad MSR designs to predict production of IMS-relevant radionuclides. In particular, we pulled out the radio-xenon and radioiodine signatures, as well as activation products, and compared them to traditional power reactors like BWRs, PWRs, RBMKs. So for the case of continuous reprocessing of the fuel salt, the radio-xenon and radioiodine signatures were found to be indistinguishable from a nuclear explosion. I said they were having a bit of a renaissance, and that's because this is not a new idea. Molten salt reactors were developed in the 1950s by Oak Ridge. They ran 2 experiments, the aircraft reactor experiment and the molten salt reactor experiment. The aircraft reactor experiment is exactly what it sounds like. It was a small reactor meant to provide propulsion for an aircraft. The molten salt reactor experiment was a little larger at 7.4 megawatts. You can actually see a picture on the right there of a worker standing on top of the reactor core. Both of these experiments were very successful. They ran for 221 hours on the aircraft reactor experiment and more than 13,000 hours over two different campaigns on the molten salt reactor experiment. So we narrowed the designs. There are a lot of designs out there being proposed down into 4 broad categories with thermal neutrons, fast neutrons, single fluid or dual fluid. The diagrams up there at the top show graphite in yellow. The orange is the molten salt, and the green on the 2 on the right is a blanket salt that can be used for thorium breeding, that kind of thing. The bottom there shows the neutron spectra, the potential for thorium breeding, potential to use other fuels, and examples that broadly fit those categories. The bolded examples, the TMSR, Mozart, MSBR, and the DFR are all examples that we had literature values for that we could build models for. So, how do you get the fission products out of the salt? In the case of the gaseous fission products, you sparge. The molten salt reactor experiment, the diagram on the top right had what was called a pump bowl, where salt was pulled up into the bowl, forced into this toroidal ring at the top, and sprayed kind of violently out of the toroidal ring and into the salt. This serves 2 purposes. Any helium that was already in the salt when it was forced through the toroid would be stripped, releasing the gaseous fission products, and they could be pulled up into an abatement system. The high-pressure jets that were going down could then entrain new helium into the salt, which would circulate through the system and pick up more fission products on their way. Nowadays, newer designs propose something like you see in the bottom left. This was the follow-up to the MSRE, which was the MSBR, the breeder reactor at Oak Ridge that was designed but never built. It's a Venturi bubble generator. Operates in much the same manner. You're introducing very small helium bubbles, and then you strip them back out once they loop back around the reactor. Same idea, a little less violent. So any good simulation starts with parameters. The parameters we collected for the TMSR, MSBR, Mozart, and DFR were from literature sources, or where not available, were simply guessed. And we have fuel salt composition, fuel salt volume, density, neutron flux, and the power. Simulations were constructed using the couple and origin modules of scale. Only the fuel salt was considered for the fission product generation. The blanket salt was not. And simulated neutron spectra at the right there, that graph, is for the reactor at equilibrium. You can see the TMSR and MSBR there have the nice little thermal peaks in the spectra. More considerations for the simulations include reprocessing. Liquid fuel can be removed in part or whole for chemical reprocessing and recycling. The MSBR and Mozart actually have listed values for the removal rates of various isotopes down the bottom right. So those were simulated. For the sake of simplicity, this was done in a continuous fashion instead of a batch process. There's also sparging, like the MSRE. 3 of the 4 reactors include sparging in their proposals. The MSBR, Mozart, and the TMSR LF1. The TMSR LF1 has an actual removal rate proposed. So this is also assumed to be continuous in these processes for simplicity. The comparison reactors, you have to have a baseline, of course. So traditional power reactors, the BWR, PWR, and RBMK were included in the simulations. So one of the first things we pulled out and looked at were the activation products. The fuel salt itself can be activated. Any impurities in the fuel salt can be activated. And if you have impurities in your fuel salt, it is corrosive. So any corrosion products will also become activated. The top two charts there are IMS relevant isotopes. On the left is the startup to equilibrium. Most isotopes reach equilibrium in about a little over 1,000 days. The charts on the right show shutdown to 100 days later. The bottom two plots are other activation products that are not on the IMS relevant list. And this is additive, right? Your nuclear reactor looks like a nuclear reactor, except these are going to be adding on top of all your other fission products. The thing we were really interested in was the xenon and iodine that's being produced. So, if you have not seen one of these plots before, this is a discrimination plot. The dashed line going through the center is your discrimination line. On the left are signatures that would be consistent with nuclear power reactors, with isotope production facilities, hospitals, that kind of thing. Signatures on the right would be consistent with nuclear explosions. So, as you can see, the two charts on the left, we have our molten salt reactors and we have our traditional power reactors. You can read these going from the top right down and to the left. So top right is startup of the reactor. As it runs, it sweeps down and to the left, and then you hit equilibrium and you continue on that line going down diagonally. The left two plots for the xenon and iodine ratios are the case of absolutely no reprocessing, no sparging, no nothing. Turn on the reactor, let it run, like you would a traditional reactor. And unsurprisingly, it looks an awful lot like a traditional reactor. There is not a lot of difference there. Your xenon hangs out a little longer on the right side of the discrimination line, but it hits equilibrium pretty quickly, and you're on the left of the discrimination line. The real concern is those two plots on the right, where the MSBR and Mozart are doing reprocessing and refueling, and the TMSR is doing sparging. The MSBR and Mozart start on the right of your discrimination line and stay there. They do not move across when they hit equilibrium. They just stay on the right side of the discrimination plot. And this is of concern. Abatement is going to be really important if a reactor is operated in this manner with continuous reprocessing and refueling. It could really complicate the backgrounds for the IMS stations. So, in conclusion, continuous reprocessing and refueling in MSRs can create xenon and iodine ratios that remain over the discrimination line during equilibrium operation. Thank you for your attention.
Questions to the speaker?
Thank you. That was really interesting. I was just wondering whether you've considered design basis faults and the effect of the emissions in those situations and how they compare to traditional reactor faults as well.
Reactor folds?
Situations where you will either damage fuel and cause a release or
Oh,
or
yeah.
a depressurization or something like that, which would give a greater release.
Yeah, the molten salt reactors are of interest partly because they operate at ambient pressure. And if something goes wrong, if you stop the flow of fuel salt into the reactor core, your fission stops. And then it cools off and it freezes. So catastrophic failure, there's usually like a fuel salt plug that will melt and then drain all the fuel salt into a reserve tank, an emergency tank. So cracks and things like that are certainly a design consideration, but that's one of the attractive things about molten salt reactors.
Yes.
Thank you. One of the things you were showing particularly at the end was isotope ratio plots.
Mm-hmm.
Can you speak to the magnitudes of the signals that are coming off of molten salt compared to other reactors?
Yeah, that's a really good question. So the simulations are just about what's in the inventory, right? So it's not talking about releases, just what you have at the time you're operating. And as far as magnitudes, I'm sure I could pull up the plot and actually look at them because we do have the actual activities and such on there. But yeah, you're looking at the current operation. That's what I was saying about abatement there at the end. You're going to need to do it in any case for any reactors when you're off-gassing, but it's going to be interesting to see that for molten salt reactors. A lot of the designs are very early on, and a lot of them don't even talk about abatement systems or what they're going to do for sparging. So it's a bit difficult to know what that's actually going to end up looking like when one goes into operation.
Any other question? So if I may, so your result shows if the molten salt reactor runs with reprocessing, then the result of fission product release, xenon and iodine, is indistinguishable from what is happening potentially with nuclear weapon test. So as you already kind of alluded, what should be the recommendation out of this finding?
Yeah. So obviously, we're going to need to work with folks who are building these reactors and designing these reactors to properly abate things, make sure it's getting trapped up. Molten salt reactor experiment did basically a very long tube to let the gaseous fission products decay initially, and then trap them up in charcoal for a while before they actually blew them out, something like 30 days. So we're going to have to make sure that those kinds of things are, as part of the design criteria early on, because otherwise it might cause some issues.
I think that should be really emphasized.
Yes.
Because there are many vendors and startups in construction.
Yeah.
And MSRs.
There's an awful lot of them, and very few, hardly any, actually talk about this particular issue.
Very interesting. Let's thank our speaker. Thank you.
So our next presenter is Sofia Brander from Federal Office for Radiation Protection. She will give a presentation on evaluation of the phase 2 test of Xenon International on Mount Schauinsland. What can be gained from higher sensitivities and shorter sampling periods? So the floor is yours.
Thanks, Jolanta. So I am sort of revisiting the Xenon International data. So as you probably all know, the Xenon International is one of the next generation systems that have been developed, and there is an official test phase, and test phase 2 for that system took place on Mount Schauinsland, where there is a CTBT station, has been a CTBT IMS station for quite some time. So this is the location of RN33. It's quite close to the city of Freiburg, and it's up in the Black Forest. I don't know, does this work? No? Okay, it's like a mouse. So we are at 1,200 meters altitude above sea level here, and most of the radioxenon that we see is actually from IRE Fleurus, because the wind mostly blows from the northwest. The test phase, official test phase, took place from July 14th to January 22nd, 2022. And then the system ran a couple of months longer because we have snow on the mountain, and it took some time for the installation to take place. The Xenon International has a 6-hour sampling time and collects about 2.5 milliliters xenon per sample. And it has a beta-gamma measurement technique which is able to discriminate all 4 isotopes of interest: xenon 131M, 133, 133M, and 135. So these are just a couple of pictures from the installation. It was a bit of an adventure to get everything down to the station. So, yeah, you can see the stable xenon volume collected during that time in the upper plot, and we have about 2.5 milliliters per sample. And on the lower plot, you can see the radon counts. And yeah, we had like one email server outage, which accounts for this smaller. Yeah, this doesn't really work very well. Well, yeah, you can see this smaller gap in the data, and then there was a failure in the heater inside of the vacuum can, which accounted for like an 8-day outage. That was just a bit not the best planning and what sort of spares we had on site. But after that, the system ran pretty well. Okay, so to the methodology, all the data I'm showing here was analyzed with the Inspire 2.00 from CTBTO, and we did some double check. The results agree pretty well with the beta-gamma viewer software that's provided by PNNL. Samples were reanalyzed either in one of the official IMS laboratories or on site in Freiburg. We also have a noble gas laboratory that's accredited according to 17025. And here we have a sauna lab system, where we can do like a reanalysis of all 4 isotopes. And we also have this older proportional counter system where we have an MDA about 1 order of magnitude higher than with the sauna lab system. But for these higher activity samples, it works very well. So this is the result of the remeasurements. On the right-hand side, you can see the official spikes that were reanalyzed in the IMS laboratories. And you can notice that the scale is quite different. On the left-hand side, I'm showing the samples that were reanalyzed in the BFS Noble Gas laboratory, and here we have some environmental samples that were reanalyzed. So that's the blue, yellow, green, and red for the different isotopes. And then the spikes, some of the spikes were also reanalyzed in our lab. And yeah, what's pretty nice, I think, is that we also got a Xenon 135 reanalyzed in our lab. And yeah, the activity concentrations match pretty well. Yeah, there's like one outlier that you probably noticed on the right-hand side of a Xenon 133M reanalysis, but the rest, yeah, is like very good, I would say. Now to the actual activity concentrations that were measured. I'm showing Xenon 133 here, so these petrol-colored dots are what the Xenon International measured. Then we have the MDC in this dark gray, in this light gray, the LC in the dark gray, and these outage times. And then the spike data is not included here, but some of the samples after the spike got affected by the spike. So that's why you can see these yellow lines. Just, yeah, not to trust some of the measurements right after the spike, because there was actually a little bit an issue with the detector coating not working perfectly well. So we do have some memory effect here. As you can also see in this sort of MDC, looks like it's oscillating after the spikes. That's just because, yeah, there was some of the detectors were coated very well, and others had a little problem with the coating. And there you can see this memory effect. Next, I'm including the SPALAX data at the same time. So that's just 24-hour sampling. And yeah, you can see it matches very well. Okay, and now I'm including also sort of simulated Xenon. That's just STAX data from IRE Fluorus, sort of times the sensitivity of an ATM backward simulation. And this really helps, because now we have like all this, a lot more data than we used to have, right? Because we get like 4 times more samples, we have a bit lower MDC, and it's like for a medium-sized national data center, it's a bit challenging. So the STAX data really helps in this case. And here, this blue line is sort of the simulated Xenon, and then we have these light gray areas. That's when, unfortunately, the STAX monitor in Fluus wasn't working. But already, like now, if you look at these white areas, I'm not sure how well this light gray can be seen, but it's okay. Yeah, you can see that a lot of the detections can be explained, but there are also some detections that cannot be explained very well. For example, in August, like between these two dark gray areas, there's some detections that cannot be explained very well with the STAX simulation. Next, this is sort of, the upper plot is the same as I just showed, but the lower plot includes the simulated Xenon, which is based on sort of mean release, where we just have 3 different release steps. So now we can also explain some of the detections that are like in this light gray area. For example, just before the dark gray area in the lower plot. Yeah, I'm really sorry this doesn't work, the pointers. Yeah. Okay, next, Xenon 131M. Here we again have this memory effect, but we can explain the detections pretty well with the STAX data. Xenon 133M. And I will come back to the Xenon 133M in a minute, but I'll show the 135 first. And here again, you can see a lot of these detections that are just above the LC, which is, I think, yeah, let's say remarkable, or yeah, well, maybe we should discuss these detections again, because I'm not entirely sure that they are real positives. And then, for example, right in the end, you can see this pretty high peak, and that's, for example, something that we would have missed, I would say, as an NDC if we don't, like without this STAX simulation, because that's actually something that's comes probably from Switzerland, so we're not entirely sure which nuclear power plant, but that's a detection from a nuclear power plant in this case. Now back to the sample composition. Usually, or what we would see with the Spalax is sort of like no radioxenon or Xenon 133, and like we all have Xenon 133 in about 40% of the samples. Now we get this whole forest of other samples, and 131M is pretty much expected, but then we also get like these samples with, for example, only 133M, but no 133. That's a bit suspicious, I would say. So let's have a closer look at this. Here you can see the MDC of Xenon 133, which is in this reddish color in the background. And then what's plotted, like these red dots, is samples, like the activity concentration of Xenon 133M in samples that don't have Xenon 133. Like, right, we would always expect to have Xenon 133 in a sample where there is Xenon 133M, because that's just where it goes. However, these samples are all sort of just above the LC. So I would like to suggest that these are false positives, and that maybe the detector calibration was a bit optimistic in this case. I don't know. This is just judging from the data when I'm having a look as a national data center on this data. Okay, next to the ratios, I'm also plotting this forward simulated, simulated Xenon. It's a backward ATM, I'm sorry. And you can see that this works very well for the ratios, except for Xenon 131M. So we have, like even I can't really see this, I'm sorry. But on the upper left-hand side, we have the ratio of Xenon 131M over 133, and you can see that the measured values are often above these simulated values, which makes sense because we have this, well, we have a lot of hospitals in Freiburg, and we also have this special weather situation, which is like an inversion, where we have a layer of clouds between Freiburg and the station, and then this layer breaks open, especially in winter, and we sort of get like this spontaneous release, I would say, of Xenon 131M. So this explains why sometimes the measurements are above the simulated ratios, but for all the other combinations of ratios, the simulation works very well. Okay, so now I'm showing some pictures, movies really. This is just an overlay of the SRS fields of all the samples that contain Xenon 133 above 2 millibecquerels per cubic meter. And not very surprisingly, this comes from Fleurus mostly. But you can also see sort of this left and right, like some sort of arms. So some also comes from the west, some also comes from the east. This is sort of the well, a proof that what we do works. So here we have all the samples that have an expected or simulated xenon concentration above 8 millibecquerels per cubic meter at the station, and we're just looking with the same setup back, like where did it come from? Oh, it really comes from Fleurus. That's nice. And next, and I'm sorry, there's a mistake here on the slide. This is supposed to be above 5 millibecquerels per cubic meter. So this is sort of the difference between the two plots that I just showed. This is measured Xenon 133 minus the simulated, and then you can see that we have some coming from the east, some coming from the west, and it's actually, well, when I first saw this, I thought, okay, that's just one event, that like something came sort of from the east, something came from the west, and we're just overlapping everything here, so it looks nice. But actually, these are separate events, and we're going to have a closer look at them. Yeah. With this, I come to my conclusion, and we're quite happy we were able to do this test phase on Mount Schauinsland because we gained a lot of information. And in general, it's very nice to have all these additional isotopes. And about our current STUX ATM setup, it's okay quantitatively, but the ratios turn out really well. And that's very helpful to analyze these large amount of data that we are confronted with now. And yeah, obviously, most of the samples that we measure on Mount Schauinsland with the xenon comes from Fleurus. But for any others, like this sort of approach that we have had as an NDC to really look at specific cases does make sense. So yeah, we will just continue to do that with some help from STUX ATM simulation.
Thank you very much. So I propose, this was great presentation, very interesting, but I think we don't have time for questions. But at the end of the session, when we will still have time, I propose to come back with question to Sofia. Thank you very much.
Thanks.
Thank you. Now, next speaker comes from Egypt, Mr. Syed Mekhaimer. The title of his talk is Solution of the National Data Center Preparedness Exercise 2019 by using inverse atmospheric transport modeling. So he represents National Research Institute of Astronomy in Egypt.
How to bring
Please, the first slide.
Good evening. I'm sorry. It's a flip without clicking anything. So, okay. This is a presentation about the solution of National Data Center Preparedness exercise. It's the exercise prepared by Italian and German NDCs. And all national data centers participate to try to solve this scenario to measure the preparedness of national data centers. So the scenario talk about imaginary states called Recia. This state announced a nuclear accident from reactor. In the 30th of July 2019. And also one of a neighboring country called Istria. This Istria asked the CTBTO to help the state to make what's called expert technical analysis. In IMS station, we have some abnormal concentration from particulate cesium-134 and cesium-137 in 6 stations from IMS stations and 1 station from the national state Istria at Vienna, this one. As you can see, we have a very high concentration of cesium at 2nd of August. And the concentration, as we go east until China, we get the decreasing of concentration. But it's some interesting values that the concentration at China is the second highest concentration after the Vienna. Okay. We have also some interesting abnormal concentration for lanthanum and barium-140. So we have this abnormal concentration. Also, we have some. Actually, the concentration in this for xenon are frequently occur in the IM stations. So it's not abnormal, but we have some multi-isotopes. So it is interesting. So we have this abnormal concentration. And we have also what's called atmospheric backward modeling produced by IDC. It's called field of regard or SRS field. So the SRS field sometimes is misinterpreted by a colleague from SHI technology. It's considered it as a possible source region. So it's not true. It's not correct. We should be careful. Because, for example, the source SRS field from China stations actually, so I'm sorry. I should go back. Okay. I want to go back. Oh, sorry. I'm sorry. I don't know how to go back. Okay, that's good. Okay. So, for example, at that time, if the SRS field actually represent the sensitivity of some location to the concentration at the station. So, the high SRS field does not mean this is the source. This is an important point. So, how we can use this concentration value and SRS field to determine the source. So, the methodology we follow like this. Actually the relation between the observation and SRS field, I want to make okay, this one, okay. This SRS field in that equation is represented by C asterisk, and the observation value is C, and this source term. The source term in our case is unknown, so we should make inverse for these matrix equations, which is very huge dimensional equations. It's about tens of millions of degree of freedom. So it can't be you can't make inversion for this equation, but we can make a vectorization, and for each grid, we should make some correlation and estimated modeling the concentration based on the SRS field at that grid and based on the concentration. So we can estimate the source, like the equation 3. So then we calculate what's called likelihood function by using Gaussian, we make a Gaussian distribution. I'm sorry, I'm not familiar with this. Okay. So this is likelihood function. And we use Bayesian approach. The Bayesian approach using this likelihood time, we multiply this likelihood function with barrier assumption. In our exercise, we assume that all grids, all time, have the same probability. There is no, using a uniform distribution. So the value of probability in that case is 1, just 1. Okay, the results. Okay. You can see that is by going back in time, we have some colored over above the Mediterranean and nearing from it the area of reactors. By approaching the 30th of July, we have some higher probability, or higher likelihood function between 30th of July until 29th of August, 30th of July to 29th of July. Then the value decreases again. So the area of interesting is the region around the reactor, around the accident, and the time between 29th of July to 31 of July. Okay, this part of presentation actually talk about seismic solution made by our colleague Mona Abazim and Adil Sami and Islam Hamama. In this part, they solved the seismic and infrasound signals, and they determined actually 3 sources. One, pure seismic at 29th of July, and 2 infrasound in 30th of July and 1st of August. In summary, the location they determined are colored by red bullet, and the reactor is a yellow triangle. So we have 3 seismic events in that domain. Okay. We go now to zoom on the area of interest. This is the same result which we are displayed in for global scale, but this is we just zooming over. We using different scale, and by go back in time, we have very low likelihood function until beginning from 1st of August, we have some relatively high likelihood, but beginning from 30, we have a higher likelihood function, and near from one of seismic events is consistent with this, with the north seismic event, blue 1, and staying for a time, the solution staying for a time for this location. So, in that simulation, we're using only barium 140 and using FlexApart ECWF model, atmospheric models. So, if you summing make a summation of all likelihood function for all times, we can get. I'm sorry, I should go one step by one. So, we get this. This is a summation of all times, and we're using different scale to the only significant likelihood function. So the area of the possible source region or the solution, it should be in that region where the reactor is actually the red circle, and one of seismic event is a blue one, and the third two seismic event in the black actually is outside outside the region of likelihood function. So we can exclude this site. So only these two interesting reactor location and the north. So by using summation of only for 1 day between 12 to 29 July and 12:30, we just get few number of grids have a likelihood function, high likelihood function. So there's a summation of all grids. If every time we make a summation of all likelihood functions for all probability for each time we collect for all grids, and this is the time which have a significant value. And by summation, this is called the marginal PDF. By summation for all latitude on all time, but for longitudes. So the actual solution is the black and red. This is two reactors, and the most probable value is the highest pins. That's for longitudes, and that's for latitudes. We have two, one for reactor and one for seismic event. So by using isotopic ratio between cesium 134 and 137, by making the ratio for all detections, we get most of the detections are following the same decay curve, except VIP have another ratio. That means that we have actually not one source, we have two sources at least. So the same conclusion we can get from the ratio between lanthanum 140 and barium 140. We have two decay curve, so we have two sources at least. So we can conclude that particulate detection in NBE 2000 exercise represents an actual nuclear event not previously seen in IM history. The Xenon detection in that exercise actually frequently looks like background, but we have some isotopic ratio not familiar. The inverse modeling by using all anomaly particulate detection shows that there is another possible location north of Triga reactor. Radionuclide isotopic ratio, and that shows that there are two different sources at least. Seismic event of infrasound technique determines the shock wave in the area of interest. Two purely infrasound, one seismic. Only the north seismic location is consistent with ATM inversing. The location is consistent with atmospheric inverse modeling using all available particulate. So the solution, our solution, actually, we have two locations. Can interpret the concentration of IM station, announce trigger reactor accident, and announce, we can say, nuclear test, unannounced nuclear test occurs on 29th of July, about mid-time. So mid-time, okay. Midnight, sorry. The adapted approach in atmospheric transport modeling assumes that the concentration are released from one source. But actually, the result shows that while this assumption when we modeling, but the approach can actually detect more than one source. I think there is some missing slides I present for all models. I can go back just a few seconds. So there's just one slide.
You are at the almost 15 minute mark.
This one. So this is actually very important because in this slide we're using two models, ECWF and NCIP, and by using two radionuclides, as you can see, different models give different solution, and For example, for barium 140, we have the two solution lies in the domain of high probability density function, while this is for INSEP, but while the same nuclide, by using ECBF, only one source, the north source, is detected. We have different also by using cesium. So the different isotope give different solution. So it's very important to what's called make summation or ensemble mean of all this likelihood function to get the source, as you can see. I'm sorry, that's our solution. Thank you.
Thank you very much.
Any quick question to the speaker?
I think we don't have time.
Okay, if not, let's move on to the next speaker. Thank you.
So if we will still have time after, then we can come back with questions. Otherwise, we can have questions during the poster session. So welcome our presenter of Argon 37 field system measurements, James Hayes. Yes?
Thank you. All right, before we start, everybody, if you just look around you, let's make sure that Boston Dynamics dog is not in here. Makes me a little, I don't know why it concerns me a little bit, but it's a little bit realistic. And I think the thing about that dog is that, I call it a dog because it looks like a dog, but it does exactly what it's supposed to do. You tell it to walk, it walks. It's very accurate. Every step is very precise, and there's no uncertainty in that in its what it does. If it's going across a hallway, and somebody's coming up and coming through the hallway, it doesn't care. It just is going to do its thing. And I was thinking about this, and it's a lot like the Argon system, Argon 37 system that made the measurements that I'll talk about today. I'm not going to talk a lot about the Argon system, but you know, the Argon system is very deliberate. You take a whole air sample, and it purifies argon, it separates, purifies it, puts it in a detector automatically, so it does that every time. It's very accurate. It's been measured against standards, and the uncertainty is pretty good on it. It's very repeatable. It's made a lot of measurements. And I was thinking about where we are today and what I've heard, and it seems like we've got a lot of nice new systems out there, the next generation Xenon systems, Argon 37 is coming up. And what it kind of comes down to is in data interpretation. I think that's where the future is interpreting the data that we're getting. And we saw a talk about ratios and how can we change ratios to get more information, gain more confidence that we know there's a nuclear explosion. We saw a talk about anomaly detection, and we saw a talk about backgrounds. And they're going to go up, and we really do need, and I think the future is this data interpretation. What does it mean? How do we know we have high confidence? Well, part of it is measuring backgrounds, and that's what my talk's going to be about, is some of the background campaigns we've run on the Argon system. And I will say, I want to put those legs on the Argon system so we can push a button and it can go put itself in place and we can measure it. But I'm just saying, if Tim's in here, maybe that's a future funding thing. Sorry, go ahead. I'll keep going. Oh, I have the control. Thank you. So why do we care about Argon 37? Well, it's a great nuclear explosion monitoring signature. Argon 37 is produced from neutrons hitting the calcium in the soil, and the calcium turns into argon 37, and that argon's non-reactive, just like xenon, and it can migrate up to the subsurface, and it can escape into the atmosphere. It's a very good nuclear explosion monitoring signature. It's also produced in the atmosphere, and in not just from argon 40 to argon 37, but from anywhere there's a neutron source and there's calcium, you can get argon 37. It's a hard isotope to measure. It's got a 2.8 keV Auger electron. Typically done underground to get rid of a lot of the background noise, so you can get that very low energy peak measured. And there's a lot in the atmosphere, even though for our system we need about 2 liters of argon for the measurement. It takes about 300, 400 liters of air to process it. So it's not a lot of air to get an argon measurement. Great signature. Roland and Robin have made quite a few measurements of underground measurements of argon-37. And you can see the plot there. And it varies quite a bit as and this is all activation, neutron activation of the calcium in the soil at depth. And so there you get about 2 meters, and you can get quite a bit of argon-37. So there's a background that I think really needs to be understood. And it's, again, back to gaining certainty in what we're seeing and understanding it. So for argon-37, the typical mode that we've been working in the PTS that we've been helping in is punching a hole down into the ground about 10 meters. We seal that hole up with some bentonite clay, put a sample tube down in there, and you can draw soil gas air out of the hole and see if any of that argon that was generated in the explosion had migrated up to that subsurface where you're sampling. And some will get out into the atmosphere. But what we also want to do is this hole gets sealed up, but when you're pulling vacuum on a hole, you can pull air down into the hole, and that can contain argon, especially xenon from, let's say, medical isotope facilities. So you want to get a atmospheric background sample. So when we collect samples, we want to know what the atmospheric load is and what the underground load is. And this is the system. I've given the talk on the details, and if anybody wants to talk the chemistry, I can do this after the meeting. But just real quick, if we look at the modules, the module on the left, it's a nitrogen reduction. You remove nitrogen as your first step, then you've got to remove oxygen, and then you do a final purification to get rid of any noble gases, any nitrogen, oxygen that remains. And then you put that gas into the detector with methane, and you make a measurement with a proportional counter. And our system's all automated. You can see the peak up on the top. That's a calibration standard at about 2.8 keV. So let's see. So over the years, just trying to understand the backgrounds, and also trying to understand, I think the biggest uncertainty is the lack of understanding of, I guess, the migration of the gases from the event up to the surface. What does that look like? And there's a lot of modeling going on, and I think we understand, there's a lot of understanding of known environments, but if there's a test and there's an unknown environment, when is that, what is it going to look like when that argon reaches the surface, and xenon in the case of some of the experiments. So on the left, we injected some xenon and argon into an old shot cavity and let that migrate up. We monitored how long it took and did some modeling. So just some experiments to figure out, what does it look like and how long does it take and what are the mechanisms to get the gas up to the subsurface. One of the things that we did find in the Nevada test site, the NNS site, was that there was quite a bit of argon-39 from historic tests still in the ground. And there's a publication on that. I think Brian Milbreath may have a little bit more on a poster later on. But interesting finding. It was an anomaly. And we saw the anomaly discussion today. This is an anomaly. I mean, we should have expected it, but we didn't. And we saw it, and it was an interesting find. Just, again, exercising our system, trying to understand if there's more anomalies. What do we expect for backgrounds? We've made quite a few measurements around the United States. Little red dots are where they're shown, and they're listed in our field campaigns. But the plot on the top shows that we've measured argon from the subsurface and the soil gas all the way up to, I'd say, about 120 millibecquerels per standard cubic meter. Very much similar to what Roland has published and what they saw. But it varies quite a bit, and this is all activation of the calcium in the soil and naturally made. A lot of variations, a lot to understand there, I think still. But one of the things that we also did is, as I said, we need to make that atmospheric measurement. And so we made atmospheric measurements along with a lot of those underground measurements. And typical backgrounds, 1 to 2 millibecquerels per standard cubic meter. Nothing really exciting, except the backgrounds are pretty low. It's a finding that, yeah, the backgrounds in the atmosphere, at least where we've measured, have been pretty low. And I think it's consistent with others that have measured argon-37 in the atmosphere. We wanted to also understand, though, if we could put a sampling system next to an IMS station and measure the argon-37, can we see a correlation with the xenon hits with argon that we measure? And so we put a system at RN75, just an air collection system, collected bottles of air, shipped those back to PNNL, and we ran them on the argon-37 system. And we did get some hits, the 1 to 2 millibecquerels per standard cubic meters. One thing we found was not really any correlation with the Xenon 133 that was seen at the RN75. So again, it's a piece of the puzzle. Is there correlation just in everyday samples? This one example, probably not. We don't really see any correlations. But as Sofia just got done talking about was the Xenon International test. One of the things that we did find in phase 1, when the system was at Teledyne Brown Engineering, going through the testing, were some anomaly radioxenon hits. The typical radioxenons that we see are 133, 135, 133M, 131M. But we saw the Xenon 122, 125, 127, 129M, and it was quite surprising. It was unexpected, and show some spectra here labeled of some of the hits we saw. Again, unexpected anomalies. Doesn't mean there was a nuclear explosion, but there was some sort of air activation going on nearby. And so what we did is just plot, this plots, if you're a Xenon person, you'll get this, but the boxes on the left are the regions of interest where we pull the counts out of to make the measurements. And there's one highlighted spot, region 11, that is outside of the 4 main isotopes that we look for in the IMS. And so we grab that because it would be background. And you can see the data that's plotted. When the system was in phase 1, that region had counts in it quite often during the phase 1 acceptance test. And then when it was in phase 2 up in Schauinsland, saw none. So the question was, well, okay, so we're seeing some anomalous radioxenon hits. Are we going to see any argon-37 hits? And so what we did is put a sampler, just that same air sampler, at Teledyne Brown outside the doors basically, and pulled in air, and we were looking for argon-37 with anomalous radioxenon hits. And so we sent those samples, collected samples, not a lot in this campaign, but we sent those back to PNNL and measured the argon-37, correlated those with the radioxenon from the Xenon International that was there. And what I can say is that, okay, if you really squint, you can maybe see a little bit of correlation. Okay, so there's not a lot here. It's below the detection limit of argon in a sense. But the red dots are that region 11 that are the anomalous radioxenons. And I don't have uncertainty bars for those because it's just counts in there just to see if we have the same spectra. And then the blue hits are the argon-37 measurements. And you can kind of see a plume of the xenon that came over, and we're missing an argon, unfortunately. One of the argon points that sample didn't make it into the system. But yeah, maybe there's a correlation. And okay, so nothing groundbreaking, and hopefully when you leave here, you have more questions than answers. That's my goal. We really need to understand the backgrounds. This is exciting because we want to get back and make some more measurements. We want to know if there's a correlation of air activation products that we might see in the IMS and argon-37. Expect there might be, but we just need a lot more data. And I think this probably goes across the board, the data interpretation. We need to understand the backgrounds better. And that's what we're trying to work at on this. So that's my last slide. And if you have any questions, happy to take them.
Thank you. So we have maybe time for one question.
Going back to your soil gas campaign, you had a few fairly high concentrations. Did those correlate with radon or uranium in the soil or anything like that? Or what do you think is causing those? I mean, you said they were N-alpha reactions, but where are the neutrons coming from?
So it's a great question about the radon. And so one of the methods we use to make sure we have a good hole and a good sealed hole is we'll pull gas out through a radon detector. And typically soil gas has about 25 to 50 kilobecquerels per standard cubic meter of radon. And so if we're over about 10, we know we've got a good seal. So there's no correlation with radon. It's just always high when we measure it. I don't have the radon for those specifically, but we can look them up. But it's a great question. Yeah.
Well, I think we have almost exhausted our time. But then before we close, we skipped to Q&A session for two speakers. Were there any questions you wanted to raise? Sofia and Syed. Well, I think also, yes.
I have a question to Sofia about the temporal resolution of stacking data. Did you subtract the simulated Xenon from the IRE source from the observation to find some anomaly like this?
Yeah, so the time resolution is 15 minutes. And as you saw, probably, I think there's some improvement to be done on our forward simulation because often the peaks are a bit off. So it doesn't really make sense to subtract this at this point of time, I think. We need to get better with the ATM first.
Okay, thank you. So I think this concludes our session. I think we saw some interesting talk, especially the MSR, molten salt reactor, is something, if you're familiar with the current nuclear industry development, there are many, many companies building molten salt reactors, including Bill Gates. I think some of the observations we saw from this session indicates an effort to come up with better signatures and so on, but it looks like we have a lot of work to do. And there will be 2 more sessions tomorrow and the day after tomorrow on this session 2.4. So stay tuned, and hopefully, as a community, we continue to make some progress to solve some of the questions we had from the talk we heard. Thank you so much.